Morning everybody. This week we're going to finish off the vectors chapter. We've got lots of little bits to do in this last bit of the vectors chapter. Basically for your exam you need to do all sorts of bits such as finding the distance from a point to a line. You need to be able to do that in 2 or 3 dimensions. We need to be able to find the distance from a point to a plane. We also need to be able to find the distance between parallel or something called skew lines. I think we may have mentioned skew lines before, but I can't recall totally if we have or not, so I'll assume we haven't. We're going to look at today trying to find the shortest distance from a point to a line. We're going to do this using the vector product. Tomorrow we'll have a quick look at a slightly different variant of it where we use the dot product, which can be useful and quicker in certain circumstances. And today there's going to be very few questions for you to do at the end. There's only 6 small questions for you to do at the end. Most of today is about trying to figure out where the formula comes from for the shortest distance from a point to a line. It's a perfectly simple and easy formula to follow, but if I just gave it to you and you didn't know where it came from, I think it would be pretty meaningless. And the nice thing about showing you the formula, showing you how you can derive the formula, is you find some other interesting bits out about the vector product on the way. So let's get going. So the first thing I want you guys to do today is prove the following is true. So I'd like you to prove that the modulus, or the magnitude of m times a vector r, m is a scalar, r is a vector, is equal to that scalar times the magnitude of the vector r. Okay, if you're struggling to do this, and that's a bit what I suggest you do, is say that r is equal to a, b, c, and we'll just prove it for that general case there, and then start on the left hand side and try and get to the right hand side. Okay, so let's go through this now. Hopefully you've all had a good go and a good try and hopefully been successful. So if I wanted to take the magnitude of m r, that's the same as doing m a b c, which is the same as doing the magnitude of ma, mb, mc. And that is the same as the square root of, m squared a squared, I'm just using an index law there to make that a bit easier, m squared b squared plus m squared c squared. And what you can do there is factor out an m squared out to get m squared times by a squared plus b squared plus c squared. And we're pretty much there now, because this bit in the bracket is the magnitude of r, just without the square root. And this is the product of two things. It's the product of m squared and the bracket, and we know by our Serre's laws, then that means we can write this as the square root of m squared times the square root of a squared plus b squared plus c squared. The square root of m squared is m, and the square root of a squared plus b squared plus c squared is just the magnitude of r. Proved. Good. Okay, so we're going to use this in a moment for our next bit of the proof of the formula. So what I'd like you guys to do is just write out the, I think my audio stopped there for a minute. I think I was saying what I'd like you to do is just write out what the vector product is for A cross B. Oops, amazing. Everything's changed all of a sudden. A cross B. I'll just do that now quickly. And this page, I'm particularly interested in what the area is of a parallelogram. And my parallelogram is defined as follows. I've got a vector A, I've got a vector B, I've got a angle theta between them, and obviously if I draw some extra lines on, I get something which is a parallelogram. I promise you this is a parallelogram. There we go. Just to make it a bit nicer. Hopefully when I asked you to write down A cross B, you wrote down the magnitude of A times the magnitude of B, sine theta, and then the unit vector normal to both A and B. Okay, what I want you guys to do is find out what the magnitude of A cross B is. And to do that, can you take the magnitude of the right hand side? Once you've done that, you need to simplify that slightly. And the best way to simplify it is by using what we've just done on the previous page. And then what I'd like you to do is try and think about whether this solves the problem which I'm trying to solve, which is what is the area of the parallelogram. So have a quick go at that. Have a good go for 5 minutes. If you don't want to go any longer after 5 minutes, then come back to the video. If you want a bit longer, feel free to do so. Or if you've got it within 5 minutes, then well done. Pause the video now and have a quick go at trying to think about those things. So modulus of the right hand side, use the previous page. How does it answer the question, what's the area of the parallelogram? Okay, so if I take the magnitude of the right hand side, then this mostly, well, it stays the same in the first instance when I just take the magnitude anyway. And then I recall what I've done on the previous page. The previous page says if I take the magnitude of a scalar times a vector, it's the same as that scalar times the magnitude of the vector. This is a scalar, this is a scalar, and sine of the angle is a scalar. So that must mean that we can write the right hand side out, because we've just proved it on the previous slide, as absolute value of A. So I keep using different phrases for magnitude or modulus or absolute value. I mean, they're all the same thing. Okay, magnitude of A, magnitude of B, sine theta, times the magnitude of the normal vector, the unit normal vector. That's what the n hat stands for. Okay, so hopefully you've said to yourself, well, it's a unit vector, Mr. Ball, so the magnitude of it is 1. In which case the right hand side is just A, magnitude, magnitude of B, sine of theta. Okay, so if you didn't get that far, then hopefully that makes some sense. That the left hand side, the magnitude of A cross B is just the right hand side without the normal vector on. And next I want you to think about, if you haven't already, how does this link to the question which I was after, which is what's the area of the parallelogram? Okay, so I've probably written this out slightly, if I'd written A and B round the other way, this would have been slightly easier to see. But let me just rewrite this as B times A sine theta. So if I do that, then I can quite clearly see that this is the base. And so what I'd really like is for this to be the height, because the area of parallelogram is the base times the height. For those of you who haven't seen it before, you remember the area of a triangle is half AB sine C, which sort of smells the same. It's the area of a triangle, half AB sine C, comes from actually the area of a parallelogram, and then just halved. And so in this case, this thing here, this better be the height, so let's just check it is. So let's make a right angle triangle here. That's theta. Oh, sorry, that's a right angle. So I've got the opposite side is the one I'm interested in, the height. And the only other thing I've got is the hypotenuse. And so that must mean that sine of theta is equal to the opposite, which is the height, over the magnitude of the hypotenuse, which is A. So in other words, H is A sine theta. And that's what I hoped it was. So this here, this A cross B in magnitude, gives you the area of the parallelogram. How do you spell parallelogram? And indeed, you could put a line across there. You could halve this, and it also generates area equals half AB sine C, the formula you remember from GCSE so well. Okay, so that sounds useful. Well, I say it sounds useful. It's fun and interesting. Not sure how it helps with this just yet. Shortest distance from a point to a line. Okay, well, let's have a go. Okay, so here's the setup here. We've got some line. I really shouldn't have done that. Let's do that again quickly. Got some line here, and it's R is equal to A plus lambda D. That's what we're defining it as. And we've got some point P, which is away from the line, and we're interested in what's the shortest distance between the line and the point P. So what we're going to do is we're going to mark on a point A. And this point A is given by this vector here. Okay, that vector there takes us to point A. That's why they're both called A, it's just obviously one's a little one because it's a vector. What other vectors have I got involved? Well, I've also got D. And D is the directional vector, and D takes me a little bit along the line. So there's D, and D takes me to a point which I'm going to call B. Let's just call that vector D. Okay, so what we're going to have a look at now is saying to ourselves, how can we somehow generate some perpendicular line to our line L which passes through P? Well, the easiest way to do it is by drawing a parallelogram. And the height of our parallelogram is going to be at a right angle to the line, and we could assume it passes through P, but it actually doesn't really matter. As long as it's the height of the parallelogram, it will be the shortest distance between P and the line. It will also be the shortest distance between the line and an infinite other amounts of points, but it definitely will be the shortest distance from the line to P. So, let's do some stuff then. We've got the vector D. We've got, I'm just going to move that D for a second, if I can, without doing everything else, just to here. And I could write in an angle, theta. And then the other vector is AP, the vector from A to P. Well, how do I get from A to P? Well, I need to go back to the origin first, so I need to do a minus A, and then I need to plus P. Let's assume that the point P I could get to via vector P, which defines the point. So if I was given the point P, that would just be what the vector is. Okay, so I now know that I've got vector D, I've also got P minus A, and I've got an angle theta in between them. So I can use this to find out the area of the parallelogram. I could say that the base, which is D, crossed with P minus A in magnitude, gives me the area of the parallelogram. So that equals the base times the height. Okay, so this is the base. and this bit here is the area. Okay, so if I rearrange this, then the height is equal to d crossed with p minus a all over, oopsie daisy, that should have a d on it, shouldn't it? All over d. Okay, so this formula can be used without proof, and it tells you the distance from the point to the line. And so as long as you know the directional vector of the line, you know the point that you're interested in, you write it in vector form. You know the a bit of the formula, so the bit which gets you to the line. As long as you've got those bits, then you can just bang it into this formula and you're done. So what I'd like you guys to do is have a couple of goes at doing that. So can you please, with these questions, exercise 11.2, question 1 and 2, just reading through question 1 and 2, I've realised I've forgotten to tell you something. At the start of the lesson I said you need to be able to find out the shortest distance from a point to a line in both 3 dimensions and 2 dimensions. The one we've just done is for 3 dimensions. If you want it for 2 dimensions, it's as follows. So the distance between a point pxy and the line ax plus by plus c equals 0 is the magnitude of ax1 plus by1 plus c all over the square root of a squared plus b squared. We won't look at proving that one, however I think it's probably a bit easier to prove, so if you want to have a look at it yourself then please do so. So have a quick go at those questions, question 1 and 2, there's not very many there, and tomorrow we'll look at a little bit more interesting stuff with vectors. Have a great day, and I'll speak to you again soon. Bye bye.